So, quiz 3 key by video. I have no idea if I'm on camera or not. You don't really need to see me. I'm not looking my best. So, the university, as you know, you're home for spring break or somewhere else for spring break. The university has told us to be prepared to finish the semester by video. I'm working on WebEx. I've sent you a link to my Orgo 1 videos. And a lot of times, I'm putting up some problems today. I actually think it's a pretty useful tool. I've gotten good feedback on this before. So I probably should do it anyway, even if there's not a pandemic and apocalypse outside. Beautiful day out there right now. Anyway, I've done this mechanism once in class. I'm going to do it again. You can sort of slow down and go through it. And then over on the right is problem number 2. Okay, so let's get right into it. The mechanism for this hemiacetal to acetal conversion. First of all, what are the conditions? We have a hemiacetal, we got a carbon there in an oxidation state, 2 bonds to oxygen, and we have methanolic sulfuric acid. And we get an acetal out of that. One thing to keep in mind, I think you guys, I think the green doesn't show up. I apologize. This is actually the last video I'm showing, or shooting, not the first, as I'm probably going to put it on there. So I think the green doesn't show up. I apologize for that. So what am I talking about? This is very light class. I've actually been doing this for a while. So you guys know at this point, if you dissolve sulfuric acid in water, that, I've said this in class, right? The high school way of thinking about this is sulfuric acid dissociates. Well, that's not true. The water deprotonates the sulfuric acid, and this makes H3O plus, hydronium, and HSO4 minus. And you can put a little plus in there if you want. I don't usually write the pluses. I don't like the pluses. People confuse them for charge. My charges are circled, but if you want the plus, you can. Okay? pKa of sulfuric acid is lower than the pKa of hydronium. The other way of saying that, sulfuric acid is a stronger acid than hydronium. And so this equilibrium goes essentially to completion. And everybody's okay with that. Well, methanol and sulfuric acid, pretty much the same way. All right, so really in this reaction, what we have here is CH3OH2 plus. And then the conjugate acid is HSO4 minus. Or sorry, the counterant is HSO4 minus. Okay, I don't really care. I've said this in class, I don't really care. But now that you're on video and you can go back and forth a couple of times, this mixture is that. Okay, this mixture basically gives you that reagent. I'm going to erase this now. The same way, if you see water and sulfuric acid, you have H3O plus. But so you can use, I'm going to go ahead and use CH3OH2, but you can do this mechanism by using sulfuric acid as the acid as well. When you do this mechanism, when you do these mechanisms on a quiz or an exam, I like you to use the actual molecules. If you learn this with just HA or catalytic H plus, that's fine. It's a good way to learn it. It's how I learned it. But there are real molecules here now, right? So when you go downstairs and you're doing a reaction in the lab, there's not some generic acid in there. There's whatever acid you put in. So right now, either use sulfuric acid as the acid or CH3OH2 plus. I'll draw that out now. The other thing, again, acidic conditions, you have sulfuric acid there, so at no point can you have a strong base. There can never be methoxide or hydroxide or any kind of really strong O- base. First step is to protonate the alcohol, neutralize that oxygen. I should probably stay in black here. And this is about a 50-50 equilibrium, right? I mean, it's obviously not going to be exactly 50-50, but it's pretty close. Protonated alcohol. And we also get methanol. Okay, now the ring oxygen can kick water out. Get a this is going to be a very fast reaction. A lot of people on the quiz had methanol do an SN2. That is wrong. So so this is right. What I've drawn here in black is right. We get water. So now you have one water, you have one of these, and you have usually show it that way, but in this particular reaction, again, you can't memorize this for this reaction, but or for the generic reaction. The generic? It's not a product. The general reaction, right? Methanol is a solvent here. You're not saying you got one of these methanols. You've got a flask full. So water leaves. We have one water, and we have a sea of methanol. That'll be important in a second. Okay, I've also seen people on the quiz draw methanol in as an SN2. And I talked about this in class. That's a secondary carbon. So that's going to be a slow SN2. It's a weak nucleophile. So that's slower. Weak nucleophile on a secondary carbon, that's not very fast. This oxygen pushing out water, good leaving group, and you get a delocalized cation, right? So there's a resonance structure where the positive charge is fully on that carbon. So that's a really nice cation. So leaving group leaving is fastest here. Really, you would only expect to see this kind of SN2 chemistry making an acetal if that was a primary carbon, and it's not going to. Okay, so now methanol is going to add in, at this point, again, a weak nucleophile, but a strong electrophile here. Neutral oxygen, protonated oxygen, and then we've got water, one, methanol, a bunch, and we have HSO4 minus. Okay, so things to keep in mind here. We protonate the OH hemiacetal oxygen, so it's got to be protonated here. It leaves as water. Methanol attacks with the proton on it, not methoxide. Methanol. So CH3OH here, not OCH3 minus. Pause this if you have to. It is not methanol. Is it on the screen? That'd be nice. I'm ranting and raving about something off the screen. Look at that, I can see it. So a lot of people, just some magic base comes in here and pulls this proton off and you get methoxide. And yeah, sure, that gets you done with the mechanism faster, but that is not going to form in the middle of a whole bunch of sulfuric acid. So methanol attacks, doesn't do an SN2. Methanol attacks, that proton is still on there. So that proton's got to be on there. And now you've got your pick of a bunch of different bases. Which one of these bases is going to take the proton? So seriously, in this case, again, if you use one of those bases to take the proton, I'm going to be pretty happy. That's my lot in life being an organic chemistry professor. But think about it. You've got a stoichiometric, one equivalent of H2O for every one of these acetals you're hydrolyzing. You've got methanol as a solvent, right? There's a C of it. You've got HSO4 minus, which is the conjugate base of the strong acid catalyst. So there's not much of that, and it's a really weak base. Weak base, not a lot of it, okay? So all of this means that the base that's going to take that proton in this particular reaction is going to be methanol. And this also serves to get you your catalytic cycle, right? So I used CH3OH2 as the acid at the beginning. It's catalytic and acid. And if you use methanol as the base at the end, it gets regenerated. If you come in here and you use one acid here and you use a different conjugate base here, it's not going to look catalytic. It is catalytic because it's catalytic H+, right? There's an extra proton floating around somewhere. There's an acidic proton floating around somewhere. One more time. We're going to protonate the OH in the hemiacetal to make water, which is a good leaving group. It leaves. We get a nice resonance stabilized cation that's still a pretty strong electrophile. Neutral methanol is going to attack, not methoxide. Weak nucleophiles, weak bases are all we're going to be able to manage under acidic conditions. So methanol, a weak nucleophile, is going to attack the electrophile. We get a protonated acetal, and then one of the many bases around, but almost certainly, almost every time, methanol, which is a weak base and is abundant. It's going to take that proton, we get our acetal, we regenerate our acid catalyst. Okay, that was problem number 1. Problem number 2 doesn't look real pretty. Hopefully you can see it. You can certainly bring up quiz 3 on Sakai. So we're going to start with methyl benzoate. I'm going to start by going up. Let's start with up. If you treat methyl benzoate with lithium aluminum hydride and H2O, lithium aluminum hydride is a strong reducing agent, a strong hydride reducing agent. It's going to add twice. Remember, strong nucleophiles are going to add twice to esters. So one nucleophile adds in, we kick out methoxide in this case, and then the second equivalent of nucleophile adds in. So we're going to get benzyl alcohol and methanol. Okay, so I'm going to separate these out a little bit. So again, 2 equivalents of H add onto that carbon. To the upper right, sodium borohydride. Sodium borohydride is a weaker nucleophile. And in this case, sodium borohydride will only add, it'll add H minus, just like lithium aluminum hydride. But it will only do that to aldehydes, ketones, iminium cations, that sort of thing. It won't touch an ester, so this was no reaction. Sodium borohydride won't reduce esters. All right, this was like a chapter 20 quiz. I gave you a couple of freebies and held you accountable for knowing older material. So methyl benzoate, doing it with bromine and iron tribromide. This is an electrophilic aromatic substitution from chapter 18. The ester is a meta-director. Nothing's going to happen to the ester. We're going to put a bromine on, meta to the ester. Lithium hydroxide, water and heat, so aqueous base. Heating this up, this is going to be a hydrolysis reaction. We're going to sub in OH for methoxide and then do acid-base chemistry. So this is going to end up O minus lithium plus. You don't have to write that lithium plus if you don't want to, and methanol. Okay, so trying to keep these. Same thing as above. If we use excess methyl magnesium bromide, excess Grignard, and then treat with water, the methyl Grignard is going to add in twice. It'll add in once, kick the electrons up on the O, the electrons come down, kick out methoxide, you get a ketone. Methyl Grignard adds to the ketone, and then we protonate. So double addition. And of course we get methanol as well, and usually if you don't write methanol, I'll be fine with it. Methanol is going to go off in the rotovap, you're not going to see it. So the other thing here again, double addition, excess magnesium, or excess Grignard. A couple of people ask me, where's the excess, do you have to say excess lithium aluminum hydride? Recall that lithium aluminum hydride, sodium borohydride have 4 equivalents of hydride on each one. So if you use a stoichiometric amount, you have excess. Okay, so this was that one. Same thing is on the right. There it goes. Sulfuric acid and nitric acid is just electrophilic aromatic substitution. We're going to put a nitro group on meta to the ester. All right, so then the last one, aqueous acid, heating it up. This is just like the one opposite it. This is going to be a hydrolysis, but now it's under acidic conditions. And so we get methanol from the ester component, and we get protonated benzoic acid. So benzoic acid, neutral benzoic acid. Okay, that's quiz 3. Send me any questions you have.